Alright, so today we're going to be talking about the calculus of vector functions. And before getting into the calculus portion, let me just make the notation that we're going to be using clear. So we know that we can write any vector as v is equal to a comma b, and then we're using these angled brackets. And this notation, a comma b, can also be so this vector can also be represented as a linear combination of two standard vectors. And what I mean by standard vectors is that we have a vector I, which is represented by 1 comma 0, so it kind of looks like this, just like the horizontal x-axis, and then we have the vector j, which is 0 comma 1, and then this is the y-axis. It kind of looks like that, right? And so whenever we have some vector v is equal to a comma b, we can write it in terms of a linear combination of I and j. And if you're to notice, you can kind of easily see that that's just writing it as a times this vector I plus b times this vector j. And we use this shorthand form to sort of represent the same thing. So these are two equivalent forms of representing vectors, and usually we're going to be dealing with this form when we're going to be talking about calculus and vectors. So the first thing that we want to sort of talk about is limits and continuity. And so let's just define the limit. So let r of t equal f of t of times I plus g of t times j. So essentially we have this vector valued function where we have so each vector has like a x component and a y component, right? And some functions defining the x component and other functions defining the y component. And if the limit as t tends towards c of f of t is equal to some value L1, and the limit as t tends towards c of f of t, g of t is equal to some value L2, then we say the limit of the vector function r of t as t approaches c is simply limit as t tends towards c of r of t is equal to this limit, but this is a vector now, so it's like a darker L, right? It's a bolded L, and that is simply equal to L1I plus L2J. And so essentially what we did is we sort of split our vector function into the component form, and we saw how our x is changing as a function of t, and we saw how our y value is changing as a function of t, and we found and at that point now we just have like a single variable function, right? Because this will just be like f of t is equal to x. So we have basically a function of t that defines x, and we just found the limit of that, which we already know how to do. We know how to deal with single variable functions, and we did the same thing with y, and then we kind of just concatenated it to find the to find the vector limit as t tends to c, because at the end of the day we want to find the limit of the vector. And to sort of make this more concrete, let's say we have a function r of t is equal to cosine of t I plus sine t j, and we want to find the limit as t tends towards pi over 4. We essentially just find, so in this case now we just find the limit of cosine t as t tends towards pi over 4, which is just equal to root 2 over 2. And then we know that the limit as t tends towards pi over 4 of sine t, which defines our y component, is also root 2 over 2. And therefore, we found the component-wise limits. Therefore, we can claim that the limit as t tends towards pi over 4 of r of t is simply equal to root 2 over 2i. That's coming from this limit, and then plus root 2 over 2j, which is coming from the sign, which defines the y value. So notice how in vectors, a vector is essentially just like a concatenation of multiple variables. And so to find the limit, we're now kind of dividing it up into each variable, each component, and we're just doing what we're familiar with in terms of single variable calculus on those. And this will be a trend for all sort of calculus operations, as we'll see. So that was limits. Let's talk about continuity. So a vector function, r of t, is continuous at a point t equals c if, or t equals c in its domain if the limit as t tends towards c of r of t is equal to r of c. So basically we're saying that it's like the similar definition of continuity in single variables, where we're continuous at some point c if the value we approach at the limit is actually equal to the value of the function at that point. So we have to have the point defined at that value, and in the limit we have to like reach that value for it to be continuous at that point. And like a corollary of this is the component test for continuity, which states that r of t, which is equal to f of t of I plus g of t times j, is continuous at t equals c if and only if f and g are continuous at t equals c. So now basically, again, notice how we have split the decision of whether a vector function is continuous at some point t on the decision of whether each of those single component functions are continuous at c. So to check if a vector is continuous at c, we have to basically see the single components that determine x and y, and individually check if they're continuous at c, which we already know how to do. And after we check that, if both of those functions are continuous at c, then our actual vector function is continuous at c. So notice how we split it up into individual components, and then that determined continuity. So let's say we have some vector function r of t is equal to 1 over t times I plus sine t times j. We have to determine at what values of t is this function continuous. So sine t is continuous on all real values, right? But this function 1 over t is not defined at t equals 0. So the intersection of like the points that our entire vector function is defined at is simply negative infinity to 0 union infinity, or 0 to infinity, right? And so the only point at which one of these functions is not defined is at 0. So r of t is not continuous at t is equal to 0, because at t equals 0, our function that defines the x component of our vector is not defined. And so basically the intersection of the two functions that make up our vector function is the domain at which our function is actually defined. or is the domain at which our function is continuous. So that was limits and continuity, and the next thing we sort of covered in calculus was derivatives, right? And so how do we define derivatives of a vector? So given a vector function, r of t is equal to f of t of I, so we have seen this before, plus g of t times j. This function has a derivative at t, and that's the same thing as saying it's differentiable at t if f and g have derivatives at t. So yet again, basically we have kind of left the decision of whether or not our vector valued function is differentiable on like checking each of these individual components function and checking if they have a derivative of t, and we know how to deal with that. So just the vector analogous version is just checking each component and making sure all of them have derivatives at t, not like, and if a single one of them does not, then our function is not differentiable at the point t. And so that's determining if it's differentiable. What is the actual derivative? So dr over dt is equal to the limit as delta t tends towards 0 of r times r of t plus delta t minus r of t. And this comes very similar from like the single variable definition of a derivative. And this just turns out to be df over dt of I plus dg over dt of j. And so this kind of makes sense, right? Because what we're doing is we're having this delta t, which is like some small difference away from the point t which we're at. And now that we're dealing with vectors, there's like a direction both in the I direction and a direction in the j direction. We're squeezing both of those towards 0. And so if we know the vector formulas for that, and we know how I is affected and we know how j is affected, because we have a function of t defining both of those, we can simply find the derivative of those and concatenate it to find the derivative of the vector itself. So again, very analogous to what we have seen before for all of the other limits and continuity in like the vector form. And so knowing that, we have r of t is equal to 3 cosine t times I plus 3 sine t times j, and let's find r prime of t. And if we were to follow this definition, we know it's simply finding each of the individual component-wise derivatives with respect to t and then putting it in the vector form. So the derivative of 3 cosine t is just minus 3 sine t times I, and then this is just plus 3 cosine t j. So really not too complicated. It's just us kind of getting used to the vector form of everything. And so the rules of differentiation in the vector form are also very similar to the scalar form. So it should not be too difficult to kind of get used to it, but I'll explicitly state them anyway. So the first one is called the constant function rule. And this essentially states that the derivative of some constant vector is simply equal to 0. Next one is scalar multiple. And so this is scalar multiple, so we're not multiplying by a vector. And so the derivative with respect to t of some scalar, so c some scalar times some vector v, where v is a vector, is simply equal to the scalar times the derivative of the vector with respect to t. And so it's very analogous to the single variable formats, and you'll notice this in all the rules. So the sum rule, and you can kind of guess that this is the derivative of two vectors being added, and that's just equal to us taking the derivative of each individual vector and summing them together. And difference rule is analogous, so d over dt of u minus v is simply equal to du over dt minus dv over dt. Alright, so dot product. So when we multiply two vectors together, there's two ways to multiply them. And one of these products is called the dot product, and this is often known as the scalar product. And when we're taking the dot product of two vectors, and so this is not the cross product, this is the dot product. When we take the dot product of two vectors and we find the derivative of those, you can kind of think about the product rule. So it's very similar to a product rule where we find the derivative of one vector, multiply it by the other vector, plus the other vector times the derivative of the second. And then we have chain rule. And the chain rule essentially states that dr, where r is a vector, over dt is equal to dr over ds. dr over ds is equal to dr over dt, where t is some other variable, times dt divided by ds. So we have seen this one before as well. And yeah, I think one important thing is that this product, this vector product, is the dot product, not the cross product of two vectors. So that was some of the differentiation rules. Now let's get to integrals. And so the indefinite integral of some vector function r with respect to t is just the set of all antiderivatives denoted by the integral of r of t dt. And so when we do the indefinite integral of this function r, we get some antiderivative r of capital R of t. So this is another vector function defined or a vector function of t, and then we have some constant, and then this constant is now a vector, not a scalar. And the usual arithmetic rules for indefinite integrals, which I've covered before, continue applying in this case as well. And so that's the indefinite integral. And so if we have a definite integral, again, to evaluate definite integrals, it's very similar. So if we have r of t is equal to f of t times I plus g of t times j, and we know it's integrable on this domain from a to b, then if we were to find the definite integral of r of t dt from this in this interval, that's the same as evaluating from a to b of f of t dt and multiplying it by I, and then plus from a to b of g of t dt and multiplying it by j. So the result of this, the result of evaluating an indefinite or a definite integral of a vector is us splitting it into its component-wise forms, and then evaluating it on the same interval and then concatenating them to form our vector. So yeah, let's do some practice with integrals and vectors. So let's evaluate this indefinite integral first of cosine t times I minus 2t times j, and then dt. And we know that we just have to component-wise evaluate the integral, so this is just the integral of cosine t dt minus the integral of 2t dt times j times I. And so this is simply sine t I, and then minus t squared j, and then we have like one constant vector. So like again, we've seen it before. Whenever we kind of concatenate two indefinite integrals, their constants get added. So this one big C, where C is a vector, represents our plus C in the vector case, where before the plus C was a scalar C. Now, what if we wanted to evaluate that? What if this integral was just the same, but it was from 0 to pi, right? And in that case, we already know that our antiderivative is sine t times I minus t squared times j, and now we're just evaluating that whole thing from 0 to pi. Therefore, sine t, sine of pi is 0, so and then sine of 0 is also 0, so we get 0 minus 0 times t, and then we get minus t squared, which is pi squared, minus 0 squared times j, and so we essentially end up with what is I? We essentially end up with 0i minus pi squared j, and that's the same thing as minus pi squared j. So really, like, finding out the integrals and the derivatives and limits and whether a function is continuous in the vector case is very similar to the scalar case, except we just split up the vector into its component-wise definitions, and now once we've done that, we now get we basically get a linear combination of single variable functions, and we've already, like, throughout this time we know how to deal with calculus and single variable functions, and so that's how we then manipulate the single variable functions and then finally concatenate together to get the vector answer. So it's really a process of vectors to components and then back to the vector, and that's how you deal with vector valued functions.